Alrighty, if you will get your notes out that we've been working on. I know what you picked up, it looks like notes, and it can be, but it's also your practice. Practice. So the re-quiz for the multiple choice tech quiz is going on, and I had several of y'all in here that need to come and just take it the first time. Juan, I know your mind, okay, yeah. So for some reason on that day, several of y'all. So there's my tutorial that has to be done before Wednesday, because that gives you some morning and some afternoon opportunities. We have one quiz this week on Thursday. It'll be over what we covered today and what we cover tomorrow combined. And I think that's it. Anybody got any questions? And we do go a full day on Friday. That has seemed to be a very popular question. It is a full day. I did double check myself. All right, so we're going to talk about covalent compounds. So covalent compounds means the electrons are being shared, 2 or more nonmetals. And we're going to get to work to drawing the Lewis dot structure for those. So start off with a little vocabulary: molecule, molecular compound. If anything that has to do with molecule is always a covalent compound. That means it held together by covalent bonds. Molecular compound is going to be the formula for a covalently bound compound. So example would be CO2. Chemical formula is used for covalent and ionic compounds. So it's like a broader term. So an example would be, we could say maybe glucose, if it's a covalent compound, or aluminum oxide if it's an ionic compound. It's just showing what elements and how many atoms of each type. So within those covalent compounds falls our diatomics. So if you haven't memorized those, now is once again the time to do that. So remember, diatomics are 7 elements, or actually diatomics are 7 molecules made out of elements that are not stable as just a single atom. So in yellow is the formulas or the symbols. Underneath it are the names. One way or another, write those 7 down if you didn't memorize them. So you will memorize them. I have some butter braids coming from somebody. Okay. Sounds good. I'll be here in the morning. If you want to get rid of them, drop them off. Or move up if that's okay. So we talked about this before. Whenever a chemical bond is formed, the nucleus of one atom, because the nucleus would be positive because of the protons, and the valence electrons, which would be negative, another atom, because opposites attract. So they're attracted to each other until the optimum or perfect distance is reached, where the potential energy is lowered and they become more stable. Remember, that's why elements form compounds instead of staying as elements. They get to be at a lower energy and become more stable. And by optimum distance, they have to be close enough where the positive and negative attraction can feel each other, but far enough apart because it's a bunch of electrons and they're going to be repelling each other. So there's like a perfect distance where they're going to be at their lowest potential energy. So if we talk about covalent bonds, we can describe them with regard to bond length and bond energy. So the distance between two bonded atoms would be our bond length. And the energy required, so that's an endothermic process. It takes energy to break bonds, and then energy is released when bonds are reformed. And bond energy is kind of can tell you how strong a bond energy is. As the bond energy increases, the bond strength also increases. So in other words, if you had a bunch of bond energy values, whichever one was the highest, that was going to be the one that was the compound that was going to have the strongest bond. So the octet rule, we've talked about that before, and that's kind of what we're going to be getting to today whenever we start drawing our structures, is the fact that chemical compounds were share, lose, or gain, so they can get that octet in their outer energy level. So an example of that, we can do diatomic fluorine. So fluorine is element number, it's in a halogen, so it has 7 valence electrons. So one short of the octet, that makes it very unstable. It's very reactive. But if I put 2 of them together, and they donate their single elements to the middle, then they will form a bond where these 2 electrons are. That's the bond right there. And by doing that, each one now will have an octet. They each had 7, and then they're now borrowing 1 in the bond from the other element, and that's going to give them their full octet. It's going to make them much more stable. There are some exceptions. Boron only needs 6 to be stable. Hydrogen and helium only need 2. And then there's also something called an expanded octet, where you have greater than 8 valence electrons. And that can happen for some elements. We're really not going to work with it a lot in Chem 1. That's more an AP chemistry or college chemistry, but that way, if you get to college chemistry and they talk about expanded octets, you can at least kind of have an idea. That means more than 8 valence electrons it's able to hold. So we're going to be doing electron dot notation. It's also called Lewis dot notation, and we're going to be putting those together for elements to show how compounds are representative. So it's a type of representation where only the valence electrons are used. And it uses a symbol, and then the electrons are represented by dots around the electrons. You can take off that 1 and that 3. The dots come from the outermost S and P orbitals. We talked about that when we were doing electron configuration. So you're going to put the symbol in the middle, and then you'll use dots to represent how many valence electrons. So for instance, that has 8 dots, 8 electrons, so that would represent a noble gas. And the electrons, when you draw them, are like on 4 sides. Sometimes I'll have people draw them real random, and it'll look like they're just doing a continuous circle around there. That doesn't work. They need to be on the 4 different sides as you start to draw your Lewis dot structures. All right, so these are elements from one element from each of our representative groups. So this is group 1, and then we get down here to group 18. So remember the elements in group 1 and 2, that's how many valence electrons they have. And then as we get to 13 through 18, you have to subtract 10. So for my Lewis dot for sodium, it's in group 1, so it has 1 valence electron. So I would put 1 dot on one side of it. It doesn't matter which side. Magnesium is in group 2, so it has to have 2 dots. And just like with electron configuration, we have to have 1 on each side before we pair up. Boron group 13, so it would need 3. 1, 2, 3. Carbon group 14, so 4, a single on each side. And finally, when I get to nitrogen, it has 5 valence electrons because it's from group 15. So now I'll do my double up. I'll still put 1 on each side. And then I'll finally be able to double up on that. So y'all finish those out, oxygen, fluorine, and neon. They just go in that same continual order. So we're going to be putting these together to represent covalent compounds is what we're working toward today. And tomorrow we'll do ionic compounds. I personally think ionic compounds are a lot easier. All right, so Lewis structures are used for represent molecules. Dashes or dots can be used to indicate a bond. And then dots will indicate lone pairs not involved in bonding. So if I have HF, it's going to have a bond in between here. So I'm going to represent that with 2 electrons. And then fluorine still has 3 lone pairs that just go around it. Here, hydrogen, each hydrogen has 1 electron, so they will share that in a bond. Remember, if a line is drawn, it's still made up of 2 electrons. And then fluorine will have a single bond, and then each one still has 3 lone pairs that they keep to themselves. If we look just at a single fluorine, that's what it looks like. So notice that the atom, in this case fluorine, keeps the 3 pairs. It's willing to donate that single electron to a bond to share, but it's going to keep its own pairs. And that's usually true. And for what we do in Chem 1, that's going to always be true. And I kind of already said this, the unshared pairs of electrons that are not involved in the bonding belong exclusively to that one atom. If you were doing a structural formula, we're doing the full Lewis dot. A structural formula only shows where the bonds are, not the lone pair. So, oops. If I just show the single bond between them, that would be a structural. That's not what we're doing. We're doing the full thing, but you may see that, like I said, in AP or in college chemistry. So single bonds are covalent bonds produced by sharing just 1 pair of electrons. Some elements can form multiple bonds, meaning they share more than 1 pair of electrons. Carbon, nitrogen, oxygen, and sulfur can do that. And those are going to be ones that you're going to want to remember that they tend to form double bonds. If we draw all of those, carbon has 4 single bonds. It doesn't have any pairs. So it's, thank you. So we can form 4 bonds. Maybe 4 single bonds, 2 doubles. Nitrogen has 1 pair and then 3 singles. So nitrogen tends to form a lot of triple bonds because it has 3 single electrons. It's willing to share those. Sulfur and oxygen both have 6, so 2 pairs and 2 singles. Besides a single bond, what kind of bond do you think oxygen and sulfur might form? Doubles, exactly, because both of them have those 2 single that they're willing to share. So that's why those elements tend to form multiple bonds. They keep the lone pairs to themselves, and then they're willing to share the single electrons in the bond. So double bonds are the sharing of 2 a pair of electrons. So it forms 2 bonds between the atoms. So this is CO2, which is a double bond between the carbon and the oxygen. And then each oxygen has 2 lone pairs that it keeps. So if you look at that, this oxygen has 8 electrons. It has a full valence. It has a 2 lone pair, that's 4. And then remember, each of these is 2. So it has 8. Same thing with this one. And then the carbon has 4 bonds. So 4 times 2 is 8. So that's how it has its valence. When I draw the rings, I'm just showing where the valence is at. That is not part of the structure. If you were asked to draw the structure, then you would just need to draw like we did at the first. That would be considered the correct Lewis structure, not with the rings. And I say that a couple times. I'll say it again on your practice, but then I still have people on test and quizzes that come in and give me a bunch of stuff with rings all around them. All right, triple bond sharing of 3 pair of electrons. Like we said, nitrogen tends to do this. So for diatomic nitrogen, we have triple bond in the middle, which is made up of a total of 6 electrons. And then each one still has its lone pair that it keeps. So this next slide, there's no blanks for it, but you can kind of write to the side of where you see single, double, and triple off to the side. It's just telling you how many electrons make up each type. So a single covalent bond shares 2 electrons. Double covalent bond is going to share 4. Triple covalent bond would share 6. So single bonds have the lowest bond energy and they're longer, so that makes them the weakest. And that increases until your triple bond. So remember, 6 electrons make up a triple bond, so there's a lot more electron density. So the atoms are going to be pulled closest together, so it's a shorter bond, which means it's the strongest. So as you increase your shared electrons, you increase the bond strength, and it decreases the bond length. There's also something called resonance structure. We won't do a lot of those. That's more kind of an AP college, but you need to know what it is and how it's represented. So resonance structure refers to bonding. Let's should be an N, molecules or ions that cannot be correctly represented by just a single Lewis structure. So they're represented with a double arrow. So ozone is 3 oxygen together. So this is one possible way. But those are all oxygen, so they all have the same electronegativity. So we don't really know, why does that electron, why does that double bond have to be there? It could have been between the first 2 oxygen. So that would be its resonance structure. It's just kind of like you just flipped it. Notice I have that double arrow to show that it's a resonance structure. And in reality, those electrons tend to actually move between those 2 electrons. You can have 2 resonance structures, you can have 3 resonance structures. All right, we're going to stop there on that. And if you'll pull out your practice. They use a little bit of those. So kind of what it starts on that first page, we've already gone over. So we're going to move more to that second page of notes where it talks about drawing Lewis dot structures for larger molecules, so for compounds. So when you're doing that, the first thing that you need to do is determine what the central atom is going to be. Hydrogen and halogens are terminal atoms, or they're always on the outer part. And if you think about it, hydrogen, and I'm just going to use fluorine, they both only have 1 single, so they can only form 1 bond, so they have to be on the end somewhere. If after that you still have to make a choice between atoms to find the central one, the atom further to the right on the periodic table is usually an outer atom. So one farther to your left on the periodic table is going to be your central atom. So if I have COH2, my 2 hydrogens would be terminal. So that gets me down to carbon and oxygen. Carbon is farther to the left on the periodic table. So it's going to be in the center. So this would kind of like be your rough draft to get you started with, without any bonds or anything like that. So the next thing you're going to do, you're going to add up your total amount of valence electrons available. So carbon has 4, oxygen has 6, and each hydrogen has 1. So that gives me 12 electrons. And that's all the electrons I have to work with those. Once I've used, if everybody isn't stable, if they don't have all their valence, then we have to start forming some double bonds. So after you've done that, you know how many electrons you have, then you're going to draw a bond between each outer atom and the central atom to start off with. So here we had a total of 12 electrons. We drew bonds between, so those took 2, 4, 6. So that took 6 electrons. I have 6 electrons to finish with. So next step is any remaining electrons are used to fill the octet of the outer or terminal atoms. So that's what we did here. We had 2, 4, and then 6. And then that used up all of the electrons. So at this point, you have to look at it and you have to see if everything is stable. Does everything have its octet? Remember, hydrogens only need 2. So on that compound written like that, is everything stable? Does everything have its octet?
Just carbon.
Carbon does not. If I look at carbon, which is right here, it only has 6. So it is not stable. So I'm not through. Whoops, let me do all that. So at this point, you look at one of your terminal atoms, whichever one has the most electrons. So that would be my oxygen. and it's going to have to donate 2 of its electrons to form a double bond. So it did that. And then whenever it formed its double bond, then now carbon has its 8, because it's going to claim all of those, all 8 of those, even though only 4 of it are really theirs, or really its. Sure, what the correct. So either drawn like this or drawn like that, that would be your representation of a good molecular compound. Notice the structure does not include these circles. The circles are just used to as a teaching tool to show you how many electrons are around the valence. All right, so let's look at a couple and walk through those on the practice. And we'll just start with your SiH4. On the side, on the key, when you get to it, you'll notice that you'll see some words like tetrahedral or maybe linear or trigonal pyramidal. We're not going to get to that till after Thanksgiving. So don't be worried about that right now, but we'll be able to come back to these and use it for that lesson too. All right, so let's start with that first one. I have silicon and 4 hydrogens. So I know silicon has to be in the middle because we said hydrogen or terminal. So I'm going to put that, kind of get myself a rough draft here. Now I need to do my total number of electrons. Silicon is in group 14, so it has 4. Each hydrogen has 4, so that gives me a total of 8. So my next step is to put a single bond between each central atom and terminal atom. So there we go. 2, 4, 6, 8. So that's it. That's all my electrons I have to work with is 8. So now I'll look at it. Is everything stable? Does everything have what it needs to be stable? Yes, they do, right? Each hydrogen has 2. And the sulfur is going to, not the sulfur, the silicon is going to claim all of those in the middle to get its 8. Once again, the circles are not part of the structure. The structure was before the circles. Anybody have any questions on that particular one? Because silicon is in group 14, so that means it has 4 valence electrons. So that was my first 4. And then hydrogen's in group 1, so it has 1, but I had 4 of the hydrogen. So that's where I got it from. Any other questions on that? All right, let's look at another one. Carbon tetrachloride. Once again, I'm going to put carbon in the middle because we said halogens like to be terminal. So start with my rough draft. And then I look at my electrons. Carbon, once again, is in group 14, so it has 4. And then I have 4 halogens, and each one has 7 valence electrons because they're in group 17. So that gives me a total of 32 to work with, 32 electrons to work with. So I'm going to start off and I'm going to put a bond, a single bond between the central atom and each terminal. All right, so when I do that, that uses 2, 4, 6, 8. So that uses 8 electrons up. So that leaves me with how many? 24. So now I just start putting a terminal or putting electrons on my terminals to give them a valence. So that means each one's going to need 6. 2, 4, 6. 2, 4, 6. 2, 4, 6. And 2, 4, 6. So I put 6 electrons around 4 atoms, so that would be 24. So that's it. That's all my electrons I have. Does everything have a valence now? Yes, it does. Everything's good. Each of the halogens, right. Yep. We don't want to do anything. Each of the halogens has 8, and then carbon in the middle It has 4 bonds, so that would be the 8 electrons. So that's how carbon gets its 8. All right, any questions on that particular one? All right, let's look at one that has to form a double bond. Then y'all might have a little time to work. All right, we'll look at this CS2. So once again, carbon is going to be in the middle and my 2 sulfurs on that each side. Carbon is more to the left, so it's going to be the central atom. Carbon has 4 electrons, and each sulfur has 6 because it's from group 16, so that's 12 to give me a total of 16 electrons to work with. So I'm going to start off and I'm going to put single bonds between each one. Remember, even if I draw a line, it's still 2 electrons, so that's a total of 4 electrons. So I use 4, I need 12 more, or I have 12 more. So I'm going to start putting my electrons around my terminal, my sulfur. So 2, 4, 6, 8, 10, 12. So that's all my electrons. I used them all up. All right. What's our problem on this one? Carbon, exactly. Carbon only has 2 single bonds, so it only has 4. It needs 4 more. I have 2 terminal atoms and they both have the same amount of electrons. So this one's going to donate its electrons to a double bond, and this one is going to donate its electrons to a double bond. So then when I do that, I'm going to have, and then each sulfur still has 2 electrons, 2 electron pairs that it kept to itself. So once again, I'm going to draw some circles. This would be your correct answer on that. But if we look here, that's how each sulfur has its valence. It's 8. And then oxygen has its 8 because it has 4 bonds. So 4 times 2 would give me my 8 valence. Anybody have any questions on that one? Not too bad. If you didn't have a chance to watch the video last night that I posted in Google Classroom yesterday afternoon, go back and watch that especially if you're struggling. And then there's also one that you need to watch tonight for what we're doing tomorrow. Same thing on Wednesday. So there's 2 videos you need to watch this week, on Monday night and on Wednesday night. All right, y'all got about maybe about 6 minutes or so, 6 or 7 minutes to do a little practice. Do we have questions? Anybody have any specific questions on this one? All right. So take some time, do some practice, see if you have any questions. We'll move on to ionic tomorrow and probably just have time for practice and questions on Wednesday. Won't have the quiz until Thursday.